Welcome everyone. Today we are going to explore one of the most important concepts in all of statistics, the t-distribution. Imagine you are a quality control inspector checking the weight of bread loaves at a bakery. If you know the exact historical spread of all loaves ever baked, you can easily spot an unusual batch. But in real life, you almost never know the true spread of the entire population. You only have your small daily sample. This creates uncertainty, and that is exactly where the t-distribution comes in to save the day. Let us dive in and see how it works. Now that we understand the real-world problem, let us look at how we handle it. When you use a small sample spread to estimate the entire population spread, you are essentially guessing. This guessing adds a new layer of uncertainty to your math. If we used the standard normal Z distribution, we would be ignoring this uncertainty. To account for it, we use the t distribution. It looks very much like a normal bell curve, but it is shorter in the middle and wider at the edges. This wider shape means it expects extreme values to happen more often, simply because we are unsure about the true spread of the data. This brings us to the mathematical tool we use to measure this, the t-statistic formula. Conceptually, this formula calculates how far our sample mean is from the claimed population mean, scaled by our estimated standard error. Let us look at the symbols. X bar is our sample mean. Mu is the claimed population mean. The letter S represents the sample standard deviation, and N is our sample size. When the difference between the means increases, the t-value grows larger. Conversely, if our sample size n increases, the standard error shrinks, which also makes the t-value larger for the same difference. This scales our difference into standardized units. Before we move on, let us see this with a concrete example. A factory claims their light bulbs last exactly 1000 hours on average. A quality inspector tests a small sample of 16 bulbs. The sample has an average lifespan of 980 hours and a sample standard deviation of 40 hours. We need to calculate the t-statistic to see how far off this sample is from the factory's claim. We chose this formula because we only have the sample standard deviation, not the populations. We substitute our given values into the formula. Next, we simplify the numerator by subtracting the means, giving us -20. And we simplify the denominator by taking the square root of the sample size, which is 4. Continuing with our calculation, we simplify the denominator further. By dividing the sample standard deviation of 40 by our square root result of 4, we get 10. Finally, we divide the numerator, -20, by the denominator, 10, to get our final t-statistic. The final answer is -2. Physically, this means that our sample average is exactly 2 standard errors below the factory's claimed average. Because we use the sample standard deviation instead of the true population standard deviation, we must evaluate this -2 using the t-distribution rather than the standard normal Z distribution. Now that we have calculated a t-statistic, let us compare its critical cutoff values against a standard z-test. Suppose we are conducting a two-tailed hypothesis test and want to be 95% confident in our results. We have a very small sample size of 9. First, we must determine the degrees of freedom for our t-test, which tells us which specific t-distribution curve to look at. We calculate this as the sample size -1, giving us 8 degrees of freedom. Next, we note the critical value for the standard normal z distribution at a 95% confidence level, which is a well-known constant, 1.96. Continuing our comparison, we now look up the critical value for the t-distribution, with 8 degrees of freedom at the same 95% confidence level. The final answer is 2.306. Comparing the two results, we see that the t-critical value is noticeably larger than the z-critical value. This perfectly illustrates why the t-test is necessary. Because the z-test assumes we know the exact population spread, it sets a lower hurdle. The t-test knows we are only guessing the spread from a small sample, so it forces us to clear a higher hurdle before we can confidently claim our result is statistically significant. To truly grasp why that critical value was higher, let us look at this diagram. Here we see two curves plotted on a graph of probability density versus value. The solid blue line represents the standard normal Z distribution. Notice how tall it is in the center? The dashed red line is the t distribution. Observe how it is shorter at the peak but thicker at the tails on the far left and right. This visualizes exactly what we discussed. The t distribution expects extreme values to happen more often because of our uncertainty. Those thicker tails are the mathematical safety knot that widens our margin of error. Now that we have seen the t distribution in action visually and practically, let us understand where it comes from mathematically. The student's t distribution arises when we take a standard normal random variable and divide it by the square root of a chi-square random variable that has been divided by its degrees of freedom. Why these specific pieces? The standard normal variable represents our sample mean, centered around 0. The chi-square variable represents our sample variance, which is how spread out our data is. By dividing the two, we create a ratio that perfectly models our real-world situation, where both the mean and the variance are estimated from the same small sample. This conceptual ratio leads us to the exact probability density function of the t distribution. Conceptually, this formula calculates the likelihood of different t values occurring. Let us break down the symbols. F sub t of t is the probability density at a specific t value. The Greek letter nu represents the degrees of freedom, which dictates the exact shape of the curve. The symbol gamma is the gamma function, which handles the complex factorial math required to keep the total area under the curve equal to exactly 1. Notice there is no exponential number e. As the value of t moves further from 0, the term inside the parentheses grows, causing the overall density to drop, creating the tails. As degrees of freedom increases, this morphs back into the normal bell curve. Now that we have seen the final formula, let us prove where it comes from. We begin our derivation by defining the two mathematical building blocks we just discussed. Let the variable z represent a standard normal random variable, which has a mean of 0 and a variance of 1. Let the variable u represent a chi-square random variable with new degrees of freedom. We must strictly assume that z and u are completely independent of each other. We write down their individual probability density functions. The PDF of z involves an exponential function of z squared, while the PDF of u involves the gamma function. These two equations are the starting point for our combined system. Continuing our derivation, we need to find the combined probability behavior of these two variables. Because z and u are independent, we can find their joint probability density function by simply multiplying their individual equations together. This is a fundamental rule of probability for independent events. By multiplying the constants, the polynomial terms, and combining the exponents, we get this joint probability density function. This equation shows the likelihood of both the standardized sample mean and the sample variance occurring simultaneously. This sets the stage for us to introduce our t-statistic transformation in the next step. Now we introduce a mathematical transformation to create our new t variable. We define t as the ratio of z to the square root of u divided by its degrees of freedom. We also define a dummy variable w, simply equal to u, to keep our two-variable system balanced. To shift our mathematical perspective from the z and u coordinate system into the new t and w system, we express the old variables in terms of the new ones. When we transform variables in probability, we must account for how the area of the probability space stretches. We do this by calculating the Jacobian determinant of our transformation, which gives us the square root of w over nu. With our transformation equations and our Jacobian stretching factor in hand, we can now write the joint probability density function for our new variables, t and w. We take the original joint equation, replace every z and u with their equivalent expressions in terms of t and w, and then multiply the entire equation by the absolute value of the Jacobian. After simplifying the algebra, we arrive at this complex formula. This equation perfectly describes the simultaneous probability of our t statistic and our sample variance occurring together. But we only want the probability of the t statistic, which leads us to our final step. To reach our final result, our ultimate goal is to find the probability density function for the t variable alone, without the dummy variable w cluttering the equation. We perform a mathematical process called marginalization. This involves integrating our joint equation with respect to w over all possible values, from 0 to positive infinity. By integrating out the w variable, we are essentially adding up all the probabilities across every possible sample variance. This integral perfectly matches the format of a well-known mathematical identity called the gamma integral. By applying its rules, the complex integral simplifies beautifully into our final result, proving the exact probability density function of the student's t distribution. We have covered a lot of ground today, so let us summarize the most important ideas. First, the t distribution is your go-to tool when estimating the mean of a normally distributed population using a small sample where the true spread is unknown. Second, mathematically, it is derived from the ratio of a standard normal variable to a chi-square variable. Third, because it relies on limited data, it features heavier tails than the standard normal distribution. This unique shape makes it a more conservative, honest, and accurate tool. It is the absolute backbone of modern practical statistics, acting as a safety net against false discoveries. Great job following along with this complex derivation.